So, welcome everyone to the Hangover on ARM64 presentation. ARM64 because Hangover can also run on some other architectures. It's more or less a history lesson and how we went from highly experimental to now basically upstream, and we just are building things and adding some new features, of course, but it's not that highly experimental anymore. So, Stefan will now tell a bit about the early days.
The early days. Let me see if I can work this keyboard. I presented my Hangover Thanks based thing back in 2017 at WineConf. I think we were in Poland at the time. And back then, that was before Microsoft had publicly announced the emulator. It was based on on auto-generated but heavily manually adjusted dunks of the Win32 API to jump in and out of QEMU. What I wanted to find out is how much impact it has if we pull the Linux user space and as much of Wine as possible out of the emulator into native code, as the predominant idea of running Wine on ARM at that time was QEMU's user space emulation, the thunks at the Linux syscall level. The secondary idea was, since there were ARM Windows devices, but no public way to run Intel applications on them, to design this entire thing in a way that could theoretically also work on Windows. We never ran this on Windows. That was just a theoretical idea at that point. The results I learned from that is essentially, performance-wise, if your emulator is too slow to run your application plus Wine, it is too slow. Pulling Wine out of it, pulling the Linux user space out of it, does not make a slow emulator suddenly usable. The one bit where taking the Wine and Linux libraries out of the emulator does have an impact is 3D graphics and to a lesser extent sound. So in some games I got a noticeable performance improvement with my direct sound wrapper instead of having direct sound in the emulator. That was mostly because QEMU's floating point performance is terrible. QEMU's performance is terrible in general. And thinking at the Win32 level, there are some bits and pieces in an API that no matter how smart you manually write your code, you can't get it to work. You can hack it around, I got things running, but it's ugly. Someone, your part?
So, yeah, as Stefan already mentioned, so the basic idea was at first, before we had any emulator integration, we had to jump out of emulation on the Linux syscall interface, which is very low level. So Wine and everything was emulated. Then Stefan's solution was to jump out of the emulation at the Win32 API level, which is very, very high level, and it's a lot of functions and it's not easy. So at some point, Wine came up with a solution called WoW64, which is basically what Windows does, and we implemented it because there was a need to get rid of the 32-bit dependencies. At least that's what I understand, and Jacek and Alexander were working a lot on that. So when that was ready, I think quickly or shortly before Wine 8, I started experimenting with it, with some patch sets floating around from Jacek and so on. And of course, we first tried QEMU, so that was the natural choice to try out an emulator. The downside is that it's quite hard to integrate QEMU in anywhere. It's just really, really, really hard. And so my first approach was to use it as a Unix library, and use the Unix lib functionality of wine to call into it. And to shorten my iteration cycles, I first tried to get ARM32-bit software running on AMD64 using the WoW64 system and QEMU as an emulator, because compiling on AMD64 and all that stuff is quite quick compared to the other way around. Suddenly I had some application running through it, and it was quite amazing, and led to everything else, I would say. But yeah, as I said, QEMU is really, really hard, and also really, really slow, so we need something else. And yeah, so at some point, other emulators which were more focused on ARM64 popped up. There was FEX, there was Box, and I also started integrating FEX, which is a C++ code base using the Unix lib integration, and suddenly it was more stable than QEMU because it's easier to integrate. So I made less errors, I think, and it was a lot faster because it was specialized on the ARM64 CPU and not generalized like QEMU was. A bit later, there was also the Box64 integration. That was now also part of the wine tree and built as part of wine, like we are doing with a lot of dependencies. And it was based on earlier work from Alexander. He did that with Box86, mostly for the non-Dynarec thingy, I think, for the interpreter. I'm not sure, it's been a while.
It worked on 32-bit. 32-bit worked with JIT.
Okay.
Not 64.
Yeah. So, for all that WoW64 building and such, it's also very important to have all the compiler support. So, thank you, Martin, for providing LLVM. MinkW, that's very handy, can build for a lot of weird Windows architectures. And yeah, I think there was some confusion about why Hangover uses Box64 to run 32-bit applications. So the simple answer is Box64 generates code for ARM64, where Box86 generates code for ARM32. And we want it for ARM64, so we need Box64. But at first, Box64 wasn't able to run 32-bit x86 applications or code it. And that was added quite quickly, more or less, by Sebastien. And so yeah, that's all the confusion stuff with why we are using Box64. Packaging was then another major topic because users don't want to build Hangover. It's a bit complicated. It consists of many components, and then at some point we had finally packages. It's interesting to look at the download statistics for those. That brought me to the interesting use cases below. Yeah, and it's more or less the only good way currently to get Hangover if you want an ARM64 build of wine. Because as far as I know, maybe something changed, but I think there are no Wine HQ ARM64 builds as packages right now. For one specific version, I suddenly had a huge spike in download, and that was, I traced it down by Googling, that specific version. So I found a GitHub project called Tiny Computer. That's quite interesting. It's Linux running in user space on Android, so no root required, and it's completely for the Chinese market. And they also seam it sometimes so that it looks like Windows, and they have Hangover on it to run Windows applications. And yeah, and suddenly I think that specific version is over 15,000 downloads. So we have 15,000 people in Asia running Hangover on their phone, it seems. That's quite interesting, at least. The other use case I want to talk about is Rhizomatica. I'm pretty sure I'm pronouncing that totally wrong. And that was a couple of years ago. Someone approached me. He is working for a non-profit organization, I think it was, that builds radio systems for indigenous people and people without easy access to communication, internet, and such. So for rural areas in Brazil, in Africa, so that different tribes, for example, can chat with each other, can share resources, like yeah, talk about resources, like we have some food left, do you want something like that. And all that happens over a radio broadcast, and they even can transfer files over that. It's basically ham radio, but with cheap hardware. So they are using a Raspberry Pi, and there is a software that can plug into a cheap ham radio and fetch the audio signal and convert it to bits and bytes. And that's an old Visual Basic 6 application. So that was even before .NET. And that's something they wanted to run, but they only had a Raspberry Pi. So they were using Hangover. It's still using Hangover. I don't know how many installations there are, but I think that's worth mentioning, that Hangover is running on some radios in the jungle. So another topic, at some point there was some guy from Cassia, which was a project, reaching out to me because they also wanted to run Windows applications on their smartphones, basically games, and they plan to also use Fax and Wine for that. And someone found out that Hangover is already doing that. So we worked a bit together. Most work was done by Billy. And yeah, Cassia didn't end up as a real project. Never was released, except now it's open source. And the good point was just they found out about Hangover. They didn't do the work twice I already did with Fax integrating into Wine. And yeah, let me hand it over to Billy. He will tell you about a bit more about it.
Yeah, so I kind of got involved with Vex and Hangover, kind of coming in wanting to kind of play PC games on Android. And then I got sidetracked and just started doing stuff with Wine and Vex for a couple of years. So yeah, I'm just going to kind of go through what Vex is and how we integrate into Wine, kind of into a bit more detail, and then how we're working with both x86 support and x64 support. Yeah, so Vex is a user mode x86 emulator. So rather than QEMU, which is both kind of can emulate the kernel and it can emulate user mode, we just focus on user mode. We're written in C++, and we support both Linux user space emulation, so you can run x86 Wine, x86 Linux games underneath Vex. And in this case, we have a funking layer that we kind of all put ourselves. that allows us to avoid emulating x86 Mesa. We can call directly into ARM Mesa. Then in addition to that, kind of what I've been working on is the Windows emulation layer. So this uses ARM64C, which I'll talk about later, and then WineConf, which André kind of described earlier, to hook into ARM Wine specifically. And in that case, the Unix core layer is used as func, so we don't need to use our own infrastructure, we kind of get that for free. We're mostly focusing on modern ARM64 platforms. We don't really kind of care that much about RISC-V, we don't care about older ARM platforms, we just want the best performance on kind of modern ARM hardware. So we use the latest extensions, that kind of thing. And we want the best performance, the best compatibility, and then ideally we don't want to have to tune hacks for every specific game to kind of get that performance. So I'll start with WineConf64. This is used for 32-bit x86 applications, and initially I kind of based this off André's port that used the Unix dev architecture. Then we kind of quickly realized, because of things like exception handling, self-modifying code, without doing a lot of kind of hacks to work around Wine, the easiest way by far would to switch to just being a PE. So kind of like what Microsoft is with their chip that they have for Windows and ARM. We do similar, and that allows us to kind of avoid us having to go around any hoops. In addition to kind of what André did initially, I kind of extended support for more complicated features like self-modifying code. And then the big thing, which is most of the work, is thread suspension. Because with a traditional WineConf or even new style WineConf on x86, because the x86 context at a given point is kind of like a subset of the x64 context, and there's one x86 instruction is still one x64 instruction. Thread suspension just kind of works as is. You can just send a signal to a 32-bit process and get an x32 context from that. But with FEX, because we're kind of emulating, we're translating an ARM instruction, an x86 instruction into multiple ARM instructions. There's no kind of defined register mapping, and we could even say we compile encode at a given point. And if you try to suspend a thread that's in the compiler, we want to wait until we exit the compiler and get to a point where we can both get the context and resume from there with you do separate context. We ended up implementing this using a callback that WineConf provides, and in this we do a kind of cooperative suspend dance. So the suspender thread that initiated the suspend will protect a threadless page as read-only. The thread that's being suspended will then kind of write to that thread at the start of every block in the JIT. So in every compiled block where we know the register state is in like a defined place, we'll store to that page. Normally it will be protected as read-write, so we won't hit an exception. Everything will work fine and we avoid any performance overhead. But if we do hit an exception, we can serialize our context, set that to the WineConf infrastructure, and then we can set the JIT up so that we can resume when we get an NT machine. So it's quite complicated, and especially because we need to support this, say, when we're entering system calls, when we're exiting system calls, when we're compiling code, lots of weird atomic state tracking and signal fences and all sorts. But it does work very well right now on it, being in the process of being upstreamed. So it's quite good. Then the layer that we use for x64 support is called ARM64C. This is a lot more complicated, but it's based off the approach that Microsoft uses for their Windows and ARM x64 support. It's basically an entirely new API that allows you to call from ARM code into x86 code and vice versa. And rather than manually authoring functions as Hangover did, the compiler itself will do all that work for you, even for like complicated cases like variadic functions and that kind of thing. And say you can patch and even if a game patches kernel 32 with x86 code, and then you have some ARM code that calls into that same function in kernel 32, the JIT will still be invoked to properly run the patch rather than skipping the patch. So it's very much caters to almost every use case. The FEX side changes for this were a lot more significant because it's basically, in addition to building WineConf64, it's a whole new API. So we need toolchain support and wine support for this. Very much thank you to Jacek and Juilliard for kind of getting most of this upstream and working on LLD support in the linker. And in terms of the changes to FEX itself, the main things were updating the register mapping, so you can call from an ARM function to an x86 function, vice versa, without having to shuffle registers around. So the first ARM parameter register is the same as the first x86 parameter register. So the only thing we need to do when we enter the JIT is to pivot the stack pointer and update some like state to kind of track that. And then I think the only other thing is also jumping in and out of x86 code. The way this is done is a bitmap that's maintained by NTDLR that kind of indicates if a given page is ARM64AC, so native ARM code, or if a given page is x86 code. And then we get an indirect branch. We can look up in that bitmap. If it's ARM code, we can execute the pivot procedure, and if it's x86 code, we can stay in the JIT and keep our fast paths that we would have the Linux. And yeah, overall, this kind of works to both reduce overhead, so we get native, DirectX 11, get native F audio and that kind of thing, and we don't need to duplicate libraries like you have for WoW64. So you still have a single copy of TDLR, a single copy of kernel 2, and it avoids kind of exposing another layer to user space. Yeah. So definitely one of the main technical challenges we kind of ran into when doing this is that FEX depends a lot on libc++, the STL, libc, and JIT modules can't really depend on that. Initially, I had some hacks to do so, but everything kind of falls apart the moment, say, a game uses x86 CRT, right? Because then FEX, when it's compiling code, will fall in CRT, but then it will try and translate an x86 function in CRT to compile the function in CRT, and you get this infinite loop, which just falls apart. So to fix that, we kind of ended up having to implement our own Windows API replacement and our own libc replacement that's kind of just depends on NTDLR, and we can statically link in. It's very much just catered to VEX. If you call a single function with the wrong argument, it will explode and you'll get a set. But it does the job that we need. And even if it's kind of ugly code, we pull in bits from Musel and all over, it works. Which is a lot better than the state before that. And yeah, here's where we're at. This game released 2 days ago, and it works perfectly fine under ARM64 VEX. This is with Windows Steam. And also, a good point this is it uses Dösinger, which is like a complicated DRM scheme that uses submodal code. Submodal code like the next instruction, so if you like increment the instruction that follows this instruction. And then lots of weird dependencies and like Windows internals and direct system calls, and all of that manages to work fine with this layer. And yeah, I guess I thought I'd say a bit about kind of the challenges here, that we still have to be problems to be solved that aren't really something that kind of one side or kind of we need to kind of collaborate on. And the main thing is that ARM64 itself isn't perfect because it's not just directly using the x86 DLLs. There are cases where games can kind of see that this isn't a regular platform. For example, the DLLs in System 32, they're to support ARM64 like regular applications and support ARM64 applications. They're compiled in this kind of hybrid format, which supports both of them. And on disk, they're stored as ARM64 binaries, or in this kind of package called ARM64X. And then when they're loaded into an x86 process, relocations are applied and they're converted to ARM64 binaries. But then if a game loads an ARM64 binary off the disk, or sorry, if the game just goes to load like System 32 DLL off the disk, it will see the ARM64 binary and it will get very confused because that's not what it's expecting. It's expecting an x86 binary. Windows solves this using like a shim that they apply in their shim database. And Wine doesn't really have any direct equivalent because for some games this might be desirable behavior to emulate. So when we read a file, we kind of patch up and apply the relocations. But for some games, we might want to expose them to the wrong DLL. So there's no kind of we can't fix it in a global way. You have to rely on application-specific hacks for this. And then a similar thing with the x86 timestamp counter. So on x86, it's kind of an order of magnitude faster than it is on ARM. This can break some games because they don't expect the timestamp to increment so slowly. VEX will rescale this, but then there's a registry key on the Windows side that needs to kind of reflect this rescaling. And it should ideally reflect that if we toggle the option off in VEX, then the registry key should hold the unscaled value, and then if we toggle the option on in VEX, the registry key should hold the scaled value. And Windows again uses a shim for this. Wine has no equivalent, so it's a bit of a problem. And yeah, in the future, we kind of want to keep on upstreaming patches most of the way there. I think so for WoW64 suspend, it's kind of awkward when you're suspending across a process because we can't just invoke on the caller a callback in the JIT to say suspend this thread in another process. We need to create a remote thread and do a weird dance there, which is quite high. And then for ARM64 EC suspend, this is a lot simpler, but still need to upstream that, and then AVX as well, which shouldn't be too bad. It's not really much code. The other thing is SV support in wine. So Vex has paths that take advantage of SV, SV2, which are kind of the latest ARM vector extensions. But these are introducing more registers for predicates that need to be saved and stored when we resume a thread. Wine doesn't currently do this, so we can't use that support. And it's kind of blocked on the Windows device that uses it, which will probably happen with the new Qualcomm laptops at some point. And yeah, just more performance improvements, more compatibility improvements. You want to run every game, that kind of thing. Yeah, I think with that, I'll hand over to the other x86 simulator. Yeah.
So yeah, I'm going to talk about Box86 and Box64. So first, what are they? So Box86 is an emulator that allows to run x86 Linux game or Linux program on ARM system, 32-bit. And Box64 came later and allows running 64-bit Linux app on 64-bit system. Simple. I will go fast because there is way too much stuff on the slide, so we don't have time. But let's talk about how it was created. So Box86 at first was created with a simple goal. I wanted to run close game on this. This is an open Pandora for those who knows, and it's a very weak ARM32 system running, like that, and not much resources, not much everything basically. So I had two objectives. The first objective is I wanted to be able to develop Box86 on this because I was traveling a lot. There is a keyboard, it's a full Linux, so why not developing on this? The second point is, I want to play games on that. So to be able to develop on that, I use some simple C and simple make system. And to be able to run games, I wanted stuff to be not emulated. So the less emulation you do, the faster you do. So basically, I started working on Box86 in 2018, but I actually worked seriously on that at the end of 2018. And in 2019, February, I had the first game running. So it's running on the Pandora. So in here, it's a screenshot of a video I made. And as you can see, it's running, you cannot see, but it's around 20 FPS. So it's not bad for a game like that. And it's especially good as when you know that there is no dynamic on that, no JIT. It's just interpreted code. And it's still 20 FPS. And it's because most of the library calls like SDL that is used for the display and OpenGL is not emulated. Everything is native. That's why it's pretty fast. So in March, I continued and then I open source Box86. Then it goes a bit faster, or not. 1 year later, I have finally the direct, so the JIT code is running, so at last it's fast for most stuff now. And I get Wine support, and Gallium 9 support, and Vulkan support, so now I had, it's not running on the Pandora anymore. I had better hardware, and in 2021, I can start Box64. Box64 is the 64-bit, and I'm using a Raspberry Pi 4 to develop. And I use all Box86 code to basically have a 64-bit, so it goes much, much faster in a couple of months. It's running, there is a direct, and it doesn't take 1 year to do that. And open sourcing in July, and I had quite some success with many pull requests and stuff. So Vulkan support is coming, Proton, so I can run Steam from Linux, and Proton is running on it. And after that, it's other stuff interesting. So later in 2023, I finally be able to add 32-bit code support in Box64. Because initially it was, if you want 32-bit, you use Box86. If you want 64-bit, Box64. But what if I want both? It's hard. So finally, the new Wo64 from Wine is running on Box64, and that opened a lot of possibilities. Also, I get RISC-V support in Box64, was interesting. And COSIM, I will talk about COSIM later, it's interesting. Another architecture coming later, that is Hauge. It's a Chinese, it's MIPS, basically, that is now Chinese. And some support for non-4K page size, because actually the Hauge was 16K. AVX is coming, 32-bit for real with Box32. That means I can run 32-bit Linux app with Box64, and so Steam, for example. And not too long ago, Box64.dll, so the DLL that can allow Hangover to run 32-bit only code. And more are coming also, and Box64, you see, at some point, that would be nice, but it's not there. So here is Horizon Zero Dawn. This is the GOG version, so just launched from the command line with Wine, and it's running on a similar machine like that. It's a big machine with a nice graphic card, but it's basically you just play like if you are on a regular PC. There is no change. 60 FPS, why not? So how Box86 was running so fast at the beginning with the Pandora is the library wrapping. So basically, it's a big difference with the traditional emulator. x86 emulator, you take your whole x86 image, you put that on the disk, and then you emulate at the syscall level, so you have everything emulated. I didn't want that for Box, so everything that is libc or something like that is not emulated, but called as native. And there are two consequences for that. The first is that Box86 or Box64 itself is built all around pthread, libc, all the native stuff. So there is no assembly level things to handle thread, for example, because I just use libc threads. And if a program wants a thread, he has a thread from libc, and that's it. No issue. So, but the issue is that if you have a a binary that is statically compiled with all the libc thread inside, well, that will not work because I'm using already the native libc. So if you have another libc, that will conflict and just fail. So that's the downside. The upside is that to run stuff, you don't need anything mostly. You just need a few C++ library because the ABI is a bit complicated to wrap, so prefer not to do that. But basically, you put a libc++.so and then you run anything. If you want to run Wine, you have nothing specific to put. You just run Wine, and it will use every library from your native system. And that's it. So it's easier to install. Basically, you just put in the binary and it works. It has easy compatibility because if you want to, support PowerPC, for example, you can just build for PowerPC. There is an interpreter inside. It will work. Slowly, but it will work. I've seen people using PowerPC 64 running some Unreal and with interpreter, and it was working. So good. The issue is that, yeah, statically compiled program doesn't work. And if you have also a program that is using like geomalloc or something like that, that are using a specific malloc, that will not work because it will conflict with the malloc that is actually using in the native libc. So we have some workaround that works, but yeah, this is kind of an issue. And the last issue is that, yeah, the wrapping of the library used all the signature of the function. So when you have a new API, I don't know, like for example, hey, WineConf has 1.4, I have to add all the new signature in the program and rebuild. So you need a new stable version to have the new API. That's a burden. One interesting thing is about, yeah, how do you debug an emulator? So the easiest way is to have an integrated debugger, and there is not. It's super complicated, actually. So what we do on Box is most of the time we dump the code that we generated, so you can just see offline, okay, what is happening with the program. And another interesting approach is the COSIM. So as I told before, there is an interpreter in Box, and there is a direct, a JIT. And COSIM allows to run both at the same time and compare the effect of each opcode on the registers and on the memory. So you see, okay, this one is trained because I don't know, EX is 5 on the side and 4 on the interpreter. So you may have some issue here. So it's an interesting way to debug the direct, especially, but that's you need also to be very patient because with COSIM you have the slowliness of an interpreter and all the bug of the direct, so it's strange. And all those tools, COSIM, dumping of code, it's available on the WoBox64, so that's interesting. And just for the fun, here is a dump. So in yellow, you have the x86 code that is just what it is. It's a part of a program. It's actually part of one. The green stuff are the metadata of the direct. Each step, some of the flags are updated, and all the optimization basically goes into the green. And the white is the ARM64 code that is emitted. And you have the same for RISC-V and Language, of course. Yeah, and the point of all the emulator is to have one white for one yellow. When we have more than one, we are not happy, but sometimes it is like it is. So this is easy to do with Box, but you have to have a lot of space because that's a lot of text file. Now, last point, what about 32-bit? Seems complicated, right? And yeah, it is. So no one cares anymore about 32-bit, it seems. It's been removed from CPUs. Modern ARM CPUs doesn't have 32 bits anymore. So basically, Box86 is dead because there is no hardware to run it anymore. So we need to use Box64 to run 32-bit. And it's complicated. And how the one you that worked on WoW64 wine, you know that it's complicated to run 32-bit in 64 because you have, yeah, everything is too big in 64-bit to fit. So that's a lot of manual work and stuff like that. So pure code, pure 32-bit code without a call to any function, that's easy because you have a 64-bit processor running 32-bit code is finger and the nose. So this one is fine. And that's why we had WoW64 support fairly quickly. And the Hangover can use that because, yeah, it's easy. The main issue is when you have function call that you have to transform, and this is box32. And here it's still experimental and it's still crashing a bit. But yeah, it's getting there. At least Steam doesn't crash too much. And here, speaking of Steam, this is Steam running Wukong. That is a de nouveau protected Unreal 5 program, and yeah, working pretty nicely. The GPU is saturated because my GPU is a bit short for this game, but that's a good sign. That means the CPU emulation is doing what it should do. Yeah. Thank you. Questions? Demo, we launched the demo at the same time.
Yeah, demo. We'll do this while we'll take questions. I'm not sure how long it takes. So.
It works through USB-C.
If you have question, maybe it depends to who the question
I
is.
think we have 2 questions.
Yeah, so shout them out and if
Yeah. So is there any solution for, or do we even want to run D3D11 implementation of 23D or D2K 32-bit on native ARM? Because with the WineConf solution, you're only going to ARM after the syscall level. Is that a factor or not?
Sorry, the question is for me.
I didn't understand the first. So the question is, I guess, 32-bit D3D11
Yeah.
applications.
Or just D3D in general, yeah.
And the issue, so the issue in particular is, I don't know how the syscall now came into the question.
Because so on WineConf you're first going to ARM code at the syscall level. So I guess like 23D or DXPK or DP3, they're all still being emulated. Is that a performance issue or not?
It's been, I don't know. It's something on my to-do list if I ever have some time to kill to try to like take a Find3D and split it into a 32-bit post-process side and pull the command stream onto the other side. So we don't call out for every Vulkan call. Old Hangover was dunking out on the D3D9, D3D10, D3D11 level, and there's quite a lot. I would also guess that like Vulkan is a bit better. OpenShell is terrible. Dunking out of the emulator on every OpenShell call is too slow. It's something to keep an eye on. It's not something I had time to experiment with. And of course, with anything 64-bit, 32-bit, there's this issue with the address space and the pointers returned from alpha maps.
Maybe let me add something on it. So for the Hangover packages, there is also DXVK built for ARM64 EC, ARM64, and yeah, the other architectures as well. So I'm not sure about the performance. I don't even have the hardware to test it on. So try it yourself.
If that 64-bit build a 32-bit version on 64EC.
There's also the x86 version that is built, so you can try that as well. But yeah,
You can speed up the 32-bit version.
yeah, maybe you can add.
Yeah, Microsoft has kind of like, they have V1 of ARM64EC that supports 32-bit, and I think that's, like, there's an option to disable it in kind of their compatibility settings. So I'm not sure how well it works, but at least from benchmarks, generally the bottleneck in old games is floating point emulation. Because of x87, it's 80-bit floats. We have to do them either in soft float, or even if we don't use soft float and we kind of reduce the precision, there's a lot of overhead from managing the stack. Because it's weird, it's old and funky. So DXVK or like WineD3D being compiled as native ARM code while shipping with WineConf probably wouldn't help that much, at least from what I expect. That's your question. Yeah.
How big is the
REC on PC.
Sorry, like in terms of binary size? Oh, performance. Because the ARM64 EC is set up such that you can convert an ARM64 context to an x86 context and back without losing registers. So because of that, there's not really enough space in the traditional x86 context to hold every single ARM general purpose register. So it reserves like 5, 6 of them that are just left unused by applications. So you kind of expect somewhat of a reduction in performance from the fact that you don't have 6 registers available for register allocation. You're going to get more stacks filling, but it's probably not that dramatic, right? Most of the, like, you have vectorized logic, that's still going to work as it would before. Most things will work equally in terms of performance. The main overhead is just from emulating x86 side code from the ARM side code. That makes sense.
And then emulating
Oh, okay. Without ARM64EC. In that case, because modern games are very intensive on like DirectX, I think I've measured like 10-20% improvements just from a native DirectX implementation, or like an ARM64 EC DirectX implementation versus an x86 DirectX implementation. So that's the kind of games that. Yeah, see, process. I think I can go with it. Full speed. 30 FPS. This is running under ARM64 EC with Windows Steam. Yeah. Any other questions?
So the turnip driver, that's for the Qualcomm GPU?
Yeah, this is running just on this ThinkPad X14 T14S, which has the X Elite X. Yeah, the X Elite 1 processor. And then it's using turnip for graphics. And just my own custom build Fedora kernel to get things to work. There's no audio, but that's just, that's the Linux problem, not my problem. That's everything. Unless there's any more questions.
That's not.
Thank you.
Oh, great.